Okay, we're going to talk about tangent lines a little bit more, definitely related to polygons circumscribed about a circle. And in this quick video, we're going to talk about tangent lines and the fact that we've got two things going on, both of which we should probably prove. Well, the first is a theorem. If a line is drawn tangent to a circle, then it will be perpendicular to the radius at the point of tangency. As well, we also have if a line is drawn perpendicular to a radius at its endpoint, then that line is a tangent. So if we think just quickly about the first one, if a line is drawn tangent to a circle, then it will be perpendicular to the radius at the point of tangency. The proof here is kind of interesting and it's quick. It's indirect. You will remember back from indirect proofs that we would assume the opposite of the proof. So let's assume that the tangent line is not perpendicular to the radius. And so therefore, that means that the radius, if we drew one in here, let's see, segment, let's put a point on the object, let's put a point there, and talk about a segment that goes from here to here. And let's assume that the point of tangency, or the end of the radius, is not perpendicular. Well, that would mean that there is, if I think about what's going on right here, and if I think about what's happening right here, if this is not perpendicular to a tangent line, I'm going to try to draw this in here. Right? So there's the tangent line. If it's not, then it can be less than 90 degrees. But we all know that if I go from A to this line here, right, there is some line that's perpendicular. So let's let it be in there. This is a little bit silly, but we're doing an indirect proof. If that's the case, look at this thing right here. This is a triangle, right? We've got a triangle from here to this point of tangency. We have it coming over, and there's a right angle. That means, of course, that this piece right here is the longest side because it's a right triangle. If this is the longest side, then how can we, it kind of falls apart over here because this is definitely longer because we're going outside the circle. In other words, there's a radius in here that is the same length as over here. And so this is the contradiction, and we find out exactly that if a line is drawn to this tangent to a circle, then it will be perpendicular to the radius at the point of tangency. And we've proven that basically by using an indirect proof, assuming that it was not perpendicular, right? And then proving that it must be perpendicular. A similar proof can be done down here. If a line is drawn perpendicular to a radius, right? Assuming that we've got a radius and that there is a line perpendicular to it, we assume, and this theorem says, then it's a line that is tangent. Well, a tangent line assumes that there's only one point where it hits the circle. We would assume in that indirect proof, which we will not do here, is that it's not tangent. Well, if a line is not tangent to a circle, then it must intersect the circle twice. So there would be another point of connection or intersection between the line and the circle. And the proof, again, you come up with a contradiction very, very quickly. Okay, so really two things that are important here about tangents. They are always perpendicular to the radius at the point of tangency. Okay, great, thanks.